Hello, everyone. Assalamu alaikum, and welcome to the Research Workplan. I am Sania, board member at ECREM and director of research and resident corner. We have come a long way, and we're finally at module 5, the one that ominously has the words data analysis typed in. Now, it may sound daunting, but don't worry, we've got two of the best people to break this part of research down into digestible concepts. So, to recap, the research work plan is designed as a modular series of lectures that altogether create a roadmap to conducting scientific research with content tailored towards EM residents in the UAE, but generalizable to all national and international physicians, residents, medical students, and interns interested in navigating research from concept to reality. So, as you may have read from our brochures, this initiative is made possible thanks to a collaboration with the team over at BEAM, Best Evidence in Emergency Medicine. BEAM is an international emergency medicine knowledge translation program created by EM physicians for EM practitioners and has the mission vision of being the most valid, reliable, and unbiased global source of current clinically relevant, patient-centered, evidence-based for EM physicians to provide the best clinical evidence to optimize patient care. We are incredibly grateful and proud to host some amazing physician researchers from the UAE and Canada who have put forth an invaluable effort to produce the content within this series.
Thank you, Sania. Hey, everyone. This is Tasnim, a board member at ECREM, and it's my pleasure to host the EBM module for today. Few housekeeping notes before we get started. Please note that this session is being recorded and will be posted on ECREM website. So you will remain muted throughout the session to minimize the background noise. So kindly use the chat box if you have any questions. We will keep track of these questions and we will present them later to the speakers in the question and answer live session by the end of the module. Finally, if you experience any technical issue, contact me directly using the chat box. So hope you all have an informative and engaging session.
Thank you, Tasnim. Without further ado, allow me to introduce our first speaker for the day, Dr. Carlos. Dr. Carlos Torres graduated medical school from Brazil in 1988, following which he completed residencies in internal medicine and cardiology in Brazil, and then emergency medicine from the Ohio State University. He has the distinct honor of being the first Brazilian physician trained in emergency medicine with extensive academic and clinical practice as a preceptor and teacher to medical students at several institutions, including the Medical School of Rio Preto, the Ohio State University, and the Mayo Clinic College of Medicine. Dr. Carlos holds a master's in medical sciences, a master's in public health, and a PhD in biophysics from the Ohio State University. He has published in several journals, including the British Medical Journal, American Journal of Physiology, Heart Circulation, Critical Care Medicine, Frontiers in Physiology, and presented at the American Heart Association, Academic Emergency Medicine, the American College for Emergency Physicians, and the Brazil Congress for Emergency Medicine, among others. He's also the Deputy Ambassador for Brazil for the ACEP and currently serves as Emergency Medicine Consultant in Cleveland Clinic Abu Dhabi. Dr. Carlos is skilled in basic and clinical research, medical education, life sciences, data analysis, with a research focus on cardiovascular emergencies. Welcome, Dr. Carlos.
Hello, everyone. Thanks for being here. My name is Carlos Torres. I'm one of the consultants in emergency medicine at Cleveland Clinic Abu Dhabi, and I've been invited to speak to you today about data management and analysis. So I've been asked to discuss a few things, primarily about data analysis, and I'm going to summarize it on the slide. We're going to speak about the purpose of data analysis. We're going to discuss a little bit about correlation. We're going to talk about the different distributions. Really important, I'd like to make sure everyone understands what the central limit theorem is. and then we'll talk about p-value, we'll discuss power and types of error, and we're going to finish up with confidence intervals. It's a lot of stuff to discuss in the little time that we have, so we're going to get started right away. So what is the purpose of data analysis? We want to use data analysis when we're confronted with something that we cannot measure, either because it costs too much or it takes too much effort, and we have to estimate or describe this. And if we want to do that, we have to use statistical analysis. Another reason, other than estimation and description, to use statistical analysis is to provide an inference. Now, an inference is nothing more, nothing less than a statement about the world. And we do that by drawing conclusions through testing hypothesis. So we'll design an experiment, and that experiment will test if our hypothesis actually corresponds to the truth. How to design that study, how to sample, how to compare, how to deal with missing data, all those aspects of study design are also within the realm of statistics and data analysis. So let's just put in a word about correlation. This is something that we all hear about, but we constantly forget. So correlation, of course, does not mean causation. There are many causes of correlation. So there are many types of correlation. Causation is a specific association between one item and another. I'd like to use the example of ice cream consumption, which is a classic example to use in terms of establishing associations. And we know, and this is a fact, that every year increased consumption of ice cream is associated with increase in obesity, higher crime rates, loss of life, and forest fires. Now, who here thinks that consumption of ice cream could cause forest fires or higher crime rates? They are associated, but the association is not causal. And the reason this happens is, as so happens quite often, both of these associations, both of these items are associated to a third factor. In this case, the hot weather. So during the summer, during hot weather, people consume more ice cream. Obesity is definitely associated with the increased consumption, but also in the summer, we see higher crime rates when people are out and about. They're swimming, they're hiking, they're doing things that are potentially dangerous. There's more loss of life, and forest fires are more common during the summer. So while consumption of ice cream is not causing the forest fires, we know it's clearly associated with it. Now, correlation always measures the strength of an association between two continuous variables. And the stronger that association, the closer we get to causation. The correlation can be measured in terms of being a very weak or a very strong correlation. The closer the correlations are to 0, the weaker they are. The closer they are to 1 or -1, the stronger they are. A correlation above 0 means that the factors, the association, the variables, they change in the same direction. A correlation below 0 means that the variables change in opposite direction. So I put down calories and weight as a positive correlation. As you increase your calories, you increase your weight. And weight and exercise is a negative correlation. As you exercise more, in theory, your weight should come down. So that's enough about correlation and causation, just something to keep in mind. I'd like to talk about the kinds of data and the kinds of distributions that are out there for us to start sampling and doing experiments. So we have all sorts of distributions in terms of our data. The data can be skewed. In other words, it can be shifted to one end of the data spectrum or the other. You can have a normal distribution where the median is straight in the middle and half of the distribution is on one side and approximately half is on the other side. You can also have distributions that are close to the normal distribution, but have an outlier. And there are many other kinds of distribution. All right, so when we discuss a distribution and when we go to describe a distribution, I need to use certain terms that summarize the data. If I want to convey to you how a certain distribution looks like, I usually use measures of central tendency and spread. So I want to describe the data in terms of where is the center of the data and how is it spread out, so you can understand the data that I'm going to use. Now, measures of central tendency and spread depend on the distribution. So if we have a distribution, for example, let me restate that. The measures of central tendency and spread, the way we want to summarize the data, depends also on the kind of data we have. So for example, if we have nominal data, in other words, I'm looking at types of data that are individual and are different, are not continuous, are of a nominal type. In other words, for example, if we're looking at ethnicity where we have Black, white, Hispanic, Asian, or if we're looking at political ideology, or we're looking at color, all those are nominal data, and we can't use average, and we can't use median for that. We have to use mode, which is basically, I'm going to tell you what the most frequent data is. So for example, in describing the population of the United States, I would say that the most frequent is, for example, white, followed by Hispanic and African American and Asian. So those are types of nominal data. If we're going to use a data set that, for example, deals with ordinal data, and that's data that's in a certain order, but not necessarily in a continuous fashion. So for example, let's say level of happiness, I can say that I am very happy, I'm medium happy, I'm extremely unhappy. Those would be different levels of data. And I would try to characterize that data by using a central tendency measurement that we call median. In other words, I would like to show what the most common or the middle number is in that data set. And if I'm dealing with data that is continuous and has an interval and a ratio, then I could use either one of them, but we tend to use the mean. We could use mode and median for that. And that's the one we're most familiar with. And that could be, for example, temperature, shoe size, test scores, hemoglobin levels. And so all those would lend themselves to a measure central tendency that we would call mean. Each one of these comes with their own measure of spread specifically for the ordinal data. If we're using a median, we want to use the interquartile range. So we're going to say, we're going to talk about quartiles. If we're talking about interval and ratio, then we can use standard deviation as a measure of spread. And just to illustrate this quickly, I have a data set here that basically represents age of patrons at a restaurant, for example. And if we remove this gentleman here who is 90 plus, we have almost a normal distribution here. And technically I could use the average and use a standard deviation. I'd be almost able to convey a good idea of this data. But once this 90-year-old walks in, everyone in this data set automatically is going to gain a certain number of years and that is going to convey a wrong description of the data. So once this 90-year-old walks into the restaurant, my average age is going to go up, probably shoot up to 40 or 50, as opposed to between 25 or 30 and 35, and it's going to give you a wrong description. So for example, in this case, it's much better to use the median, where I would describe what the most common value is, and we could use quartiles to describe the other data. So that's just an example of how you have to understand your data before you decide what to use. Now let's talk about the normal distribution, because the normal distribution is one of the most frequent that we see in natural phenomena, and also because many statistical techniques assume a normal distribution so that we could calculate and derive assumptions in understanding from the data. So in a normal distribution, the data is symmetric. The values cluster around a central region, and they sort of taper off away from the center. In a normal distribution, the mean, the mode, and the median are exactly the same. Now, the nice thing is that when you have a large number of random events, such as those that we see in nature, for example, again, hemoglobin, temperature, height, weight, any number of blood sugar values, they tend to follow the normal distribution. And that's really convenient because many statistical techniques require the normal distribution. And with that, we can use standard deviation to describe the spread. We know there are many characteristics, but we know, for example, that 95% of the data points follow between the plus and minus 2 standard deviations of the mean. And so we can use that to describe our data. Now this is really important to understand that one of the nicest things about statistics is that we're not limited to only studying data that is distributed normally in nature. The central limit theorem tells us that when we start sampling from any data set, even if that data set is not normally distributed, as our sample size gets larger, the distribution of the means of those samples become normal. And so let me illustrate that concept a little bit better. Now, if we look here to the left, we have a graph that shows a histogram that shows the number of drinks that an individual, a distribution of number of drinks by individuals throughout the year. So we have the majority of people drinking, a few drinks a year, and then this kind of slowly tapers down irregularly. And then at the end, we have people who drink every day. Now, this does not look at all like a normal distribution, and we would not be able to use our standard statistical techniques on this graph. However, if I start sampling this data, in other words, if I get 50 random samples from this data over and over again, and I sampled it repeatedly, I will start to get a graph that looks like this. In other words, the means of each one of those 50 samples, when plotted on a graph, is going to resemble the normal distribution. The normal distribution that you can see here in red is very close to the blue, which is just my repeated samplings of size 50 from this data. So what is the beauty of the central limit theorem? Beauty of the central limit theorem is that I can do an experiment without knowing the distribution of the data, as long as I do enough samples from that data set. So I can have any format of distribution of data. And as long as my sample is, as long as the number of samples that I extract from this data are large enough and the magic number is around 30, then I can use the normal distribution, the statistical techniques associated with normal distribution to describe my data.
In practice, though, we don't select repeat samples from the distribution, basically because once one sample is selected and you calculate the sample mean, as long as the sample size is 30 or more, we invoke the central limit theorem and argue that the sampling distribution of the mean is known and doesn't need to be generated. And because we know that the mean has a known distribution, then we can address any statistical questions we have.
And so with the normal distribution, we can use the normal distribution of the means to do confidence intervals. We can do t-tests when we're trying to look at the difference between two means. We can do ANOVA when we're looking at the difference between 3 or more samples. And there are a number of things that we can do with the normal distribution that are all possible because of the central limit theorem. So do not forget this. This is really important. All right, so let's talk a little bit about p-value. A p-value is used primarily to test a hypothesis. And what we do when we claim a certain p-value is we are stating, or we are asking, what is the probability that the findings that we have are due to chance? If I have a p-value of 5% of 0.05, I can say that this particular set of findings on this experiment can only happen by chance alone in approximately 5% of the time. So again, the best description I found of p-value is the p-value is a probability that the data will be just like the way it is, in other words, as extreme as it is, by chance, at only approximately the p-value percentage. So in other words, it really is a measure of the strength of the evidence against the null hypothesis. And I know this is a little confusing, but essentially the easiest way to state it is, what is the probability that what I found here is due to chance alone? And in biology and in medicine, there's sort of a convention that 5% is the acceptable parameter for p-values. Now, it's conventional. It has a bunch of problems, but it is what it is. So let's just run through a typical experiment to have a better idea of what all this means. When I set up an experiment, let's say I'm going to test a certain drug. We could say aspirin versus placebo for headache. The first thing I'm going to do is I'm going to say, okay, my null hypothesis is that there is no difference between these two groups. In other words, if I give a placebo or I give aspirin, nothing is going to happen. The true groups are going to be the same. That's how you set up an experiment. You start by stating the null hypothesis. There is no difference. The next step is we're going to give aspirin to a group, we're going to give placebo, and we're going to look at the data. After we collect the data and ask after 2 hours, how's your headache? We'd like to know if there's a difference between the two groups. And if there is no difference, the experiment is done. There's no difference. On the other hand, there is a difference, then we want to know, is that difference just because of chance alone, or is there something else going on here? And the way to do that in its most direct format is to calculate a p-value. The p-value is going to be a statement of what is the probability that the data is going to look like this if there is only chance. In other words, what is the probability these two groups are going to be as different as they are if this is all due to chance alone? The p-value is low, and that would be less than 0.05, then it's unlikely that all I'm seeing is due to chance alone. And therefore it probably isn't, and I reject the null. Now let's just talk a little bit about how this can be fraught with problems and how this needs to be set up before we even start an experiment. So for that, I came up with an experiment here where I'm playing football with this guy here. He looks a lot like Neymar. Let's say it's Neymar. And he's going to shoot a couple of penalty shots. Goes ahead and shoots 7 times, and he gets all 7 in the goal. Now, I go ahead and I hit 3 times the goal, and I miss 4 shots. And when I run the statistics on this, so I have n of 7 for each one of us, 14 shots. My p-value, sorry about that. My p-value is 0.07. Okay, so he shoots 7 times in goal and gets all 7. I hit 3 and I miss 4. I want to know if this is statistically different. What are the odds that these findings are due to chance alone? And since I established that my statistically significant difference is going to be 0.05, in other words, 5%, between my shots and Neymar's shot, I found a p-value of 0.07. So what does that mean? That means there is no difference. In other words, the experiment did not show any difference. I'm just as good as this guy at shooting penalties. So the null is true. I know everyone finds that hard to believe, and so do I. So we decided to say, what's going on here? Let's go ahead and just shoot another 7 shots at goal. And Neymar goes again, and he hits 6 out of those 7. So he gets 13 out of the 14 shots. And I go on my average. I get 3 additional goals out of the 14 for a total of 6 out of 14. So now when we run the t-test and we do the p-value, I'm going to find out that now we have a p-value of 0.013. So now there's a statistically significant difference. In other words, the experiment did show a difference between the 2 groups of shots to goal, and the null is not true. So what happened here? How could I have one data that shows one thing and the other? Well, that's very simple. And this is a very obvious and intuitive example. But the fact of the matter is that I needed more evidence. I needed a larger sample. And so that's why when you want to detect a difference and when you want to set up an experiment, once you decide on a certain p level, you have to also decide on the power of the experiment. So this leads us directly into our next slide, which is before we begin an experiment, we have to plan the experiment. We have to plan the interpretation, we have to plan the meaning, we have to decide what is significant, what is not significant, and what is a clinically significant difference as well. So there are certain terms that statisticians use, and I don't want to get into details, but an easy way to understand some of this is understand that the alpha level of a study, what statisticians call an alpha level, is nothing less than the p-value. And traditionally, we choose an alpha level of 0.05. Now, as we saw in the experiment that I just described above, the power of the experiment, in other words, the ability that I have to detect a difference, is going to depend on several things. It's going to depend on the sample size, and we just saw that with the example of the shots to the penalties. But it's also going to depend on the difference between the 2 groups. In other words, if I were a better shot at goal, and if the difference was, let's say we're testing between Neymar and Messi, 14 shots at goal probably would not show the difference. So because this difference between the two groups is small, I would have to have a larger number. And so the power of the study depends on the difference between the groups, the sample size, and also, in this case, if we have many individuals in a group, the difference between each group, each individual, and the sample mean. So the spread of the group. So in the example that we just talked about, we first found out and stated that the null was true, but we didn't have enough power. After we did get enough power, we found out that the null was not true. And what we needed was more evidence. And so these are very common errors or very common events that happen when you design a study that you have to be aware of. So let's just talk quickly about power, just to make sure that this is well understood. So power, in its best definition, is the likelihood that the test or the study that I designed is designed to detect the difference that is actually there. And the power of a test is affected by several factors. So we already saw that increasing the sample size will increase the power of the study. If I'm also looking at a smaller p level or a larger p level, I'm going to have more or less individuals in the study. Increasing the standard deviation of the population is going to decrease the power of the study, and that's logical. If I have a data that is more spread out, unfortunately, my study is going to have less power, and I'm going to have to increase the number of individuals in order to regain the power that I lost, as opposed to a data set that's very close. Now, the other issue is, what is the difference between the two groups? And so if I have a huge difference between the two groups, then I don't need a large number to detect that difference. If the difference is small, I'm going to need a larger number. Now, typically in research, we design studies that are powered for about 80%. So it means that 80% of the time, our study is going to be able to reject the null hypothesis. A little confused. Let me just try to illustrate this again with another example. Statisticians like to talk about type 1 and type 2 error. And I always find this very confusing. And I think the best image that I found to help me understand this is about the pregnancy test. Imagining that the pregnancy test is a study. So the probability of making a type 1 error, is called a false or a false positive error in terms of the test, is defined by the alpha value. So a type 1 error means that I found a significant result, but that result is not true. So for example, the type 1 error would be, this gentleman had a pregnancy test and he's obviously not pregnant. So I made a type 1 error. The chance of making this kind of error in a statistical study is related to the p-value. So once I set my p-value, I'm going to say, okay, at a 0.05 of p, I have a 5% chance of making this error, and that's okay. That's acceptable. Now, a type 2 error is when I do not find a significant result. However, there is a significant result. So that would be the individual here where I run a pregnancy test and she is not, and my result is that it's not pregnant when the person is obviously pregnant. So type 1 error is when you have a equivalent to a false positive. In other words, I find a difference when there isn't one, and a type 2 error is when I do not find a difference and there is one. That's all that is. Now, interestingly, in research, we accept 80% as an acceptable power, which means that there's about a 20% chance that I'm going to make a type 2 error. In other words, there's a 20% chance that I'm not going to find a difference when there is one. Okay, so that would be the same thing as doing a pregnancy test and saying, look, I did the test. There's 20% chance that you're not pregnant when you actually are. And that's considered acceptable in research. So again, type 1 error is defined by your alpha, typically 5%. Type 2 error is defined by your beta. We usually use 80%, and 1 minus 80 or 100 minus 80 or 1 minus 0.8 is going to give me my power. So my power is about 20%. When I try to increase my alpha or my beta, then I invariably end up having to modify one and change the other, unless I increase the sample size. So if I have the same number of subjects in an experiment, I'm looking for the same difference, my alpha and beta are going to be correlated. As I increase my alpha, my beta goes down. As I increase my beta, my alpha goes down. How do I get around that? I need to increase sample size. And sometimes that's just not feasible. So in summary, just to kind of put this into perspective, the smaller the difference, the more powerful a study I'm going to need. And usually that means, if you look here at the size of the pool, if I'm trying to look at a smaller difference, I need to increase my number of subjects, or I need to have a study duration that's longer, or I need to use different measurements. There's any number of things that can be done. And trying to detect a small difference, in other words, trying to raise the bar without changing the parameters of your study, is just not going to work. All right. So let's finish up by discussing confidence intervals. And we use confidence intervals because I'm sampling a population. And the confidence interval is the best way to measure how well this sample represents the population. I'm going to get an average or a mean of this sample, and I want to make sure that my mean of this sample here is similar to the mean of the total population. In other words, and I'm going to use a few formulas here, but in other words, confidence interval is almost like precision. I want to know how precise, how accurate my measurement is. And if you think about it, the two factors that control precision are the variation of the data. In other words, if everyone's measurement is very close, I have a very small variation, then my measurements are I'm going to need less individuals to obtain a precise measure. And the other determinant is the sample size. So if the variation is really big, I'm going to need a larger sample size to obtain the same precision. I can't change variation. Variation depends on what I'm studying, but I can change sample size. And just to have an idea, in rough terms, every time I want to double the precision, because this is a square root, I need to quadruple the sample size. So we can see how this can get really big, really fast. I'm not going to be able to work this example out in the time we have, but let's say that I put out a survey and I'm asking students if they like the new test scoring system, and I get 38% that say they like it. I calculate my precision or my confidence interval, taking into consideration the variation of the responses and the sample size that I have. And so for 100 students, I have 38% plus or minus 10. In other words, my true average, true mean could be anywhere between 28 and 48. If I don't think that's good enough and I need to get a smaller confidence interval, I need to go from 100 students to 400 students to double the precision. And so now I do the same questionnaire and I get 38 plus or minus 5, which would put the true value between 32 and 41%. Looking at this formula here, you can see that this formula is very similar to the actual formula of sample size, of confidence interval. So we have the variation represented by the standard deviation of the sample, and then we have the sample size here. And this would be the sample mean. So just again, a confidence interval is a range of values. It's a range of values that is likely to include the population, the mean population value, with about a 95% confidence interval. I could choose any number I want. It's just traditional to choose 95%. And basically, when I say it, I say I am 95% confidence that my value, the true mean, is somewhere between here and here. Another use for confidence interval is when I want to determine how confident I am that the difference that I found between two means actually lies within that number that I calculated. And so it's how confident I am that the range of values that I have represents the true difference between two means. The reason I'm stating this is what we see quite frequently in literature, and we see several studies, and we want to know if the studies represent a true difference. And to know that, and I'm talking about statistical difference, we look at the means of the two groups. For example, here we have group C and group E, and we want to know if these are actually statistically significant. And the way to do that is if the value 0 crosses the confidence interval, in other words, you have your mean here, but your confidence interval includes 0, that means that that difference may not exist and that you cannot reject the null. So when you are looking at a paper and you see groups in which the confidence interval includes 0, so if I give you a statistic and I tell you that the confidence interval includes 0, that means that I cannot reject the null. Now, and this is just as easy to understand if instead of looking at means, I'm looking at odds ratio or I'm looking at risk ratio between groups, then instead of 0, the magic number is 1. So if my confidence interval includes 1, that means that there is no difference and I cannot reject the null. Okay, why is that? Because a risk ratio of 1 or an odds ratio of 1 means that the odds are the same, the ratio is the same. All right, so one more slide on confidence intervals. And I'm sorry, this is not an appropriately sized slide, but I found it to be the best slide to represent the difference between these two. On the top part of the slide here, we have results of 5 studies, and the results are defined by point estimates. In other words, p-values, for example. And this would be study A, B, C, D, E. This would be no difference or the null, and these would be differences that we consider clinically significant. Anything above the null is statistically significant. Anything beyond this would be considered clinically significant. All right, so studies A and B, study A is not statistically significant and not clinically significant. This one is statistically significant. It rejects the null, but it's not clinically significant. And these 3 would technically be both statistically and clinically significant. Now, when we apply, so instead of point estimates, when we apply a confidence interval, in other words, I calculate my confidence interval, and that's going to depend on the spread of the data and the number of subjects in each experiment, I get quite a different picture here. So now what I have is that study A still continues to be not significant clinically or statistically. Study B also is still not significant clinically, but is significantly statistically. Now look at this guy here, study C. So this guy was way out here. And if I had just given you a p-value, you'd say, oh, this is a great study. It shows a significant difference and it's clinically significant. But when we do a confidence interval, that confidence interval means my value, my true value, could be anywhere between 0 and this number here. And therefore I cannot reject the null. And this is not statistically significant. And again, now for these 2, they're both statistically and clinically significant. So this illustrates very well the difference between reporting just p-value and reporting the result of your test statistic with a confidence interval. All right? Okay, so that's all I had for today. And in 40 minutes, we basically looked at correlation, distribution, we discussed normal distribution, we talked about the importance of central limit theorem. Again, if you remember anything from this lecture, just remember that doing multiple samples out of any form of distribution and plotting their means is going to make that into a normal distribution, which you can then use the statistical techniques that assume a normal distribution. We talked about power, talked about types of error, and we finished up with confidence intervals. So thank you very much, and I'm more than happy to answer any questions that you may have.
Thank you, Dr. Carlos, for an amazingly presented lecture on some aspects of data analysis. A lot of us are introduced to these concepts time and again during med school and then residency, but the importance of a firm grasp on how they relate to the bigger picture cannot be understated. And I think you've done a great job by going piece by piece on how different analytic components are necessary to study data and represent them in research. Thank you. Up next, we have Dr. Sameer Sharif continuing on our discussion of data analysis with his lecture. Dr. Sameer is an associate assistant professor at the Department of Medicine, Division of Critical Care and Emergency Medicine at McMaster University. He is a clinician educator and is currently completing his master's in health research methods with a focus on sedation in the emergency department and ICU. Dr. Sameer graduated from his EM residency in 2019 and completed his critical care fellowship in 2020 at McMaster University. During his training, he was recognized with the Outstanding EM Resident Award, Outstanding Critical Care Medicine Resident Award, and the McMaster Postgraduate Medical Education Resident Mentor Award. Most recently, his work was acknowledged by the American College of Emergency Physicians with the EM Critical Care Medicine Rising Star Award. Welcome back, Dr. Sameer.
Hi, everyone. My name is Sameer Sharif, and I'm an emergency physician and intensivist. I'm an assistant professor at the Department of Medicine and the Division of Critical Care and Emergency Medicine at McMaster University. I'm also a clinician educator. I'm also a researcher completing my training in clinical epidemiology as we speak. The goal today is to talk about data management and analysis. I recognize this is part 2 of a talk you guys have already had, but I want to preface this, however, by saying that my goal here is to only introduce you to a number of concepts. Some of them are fairly straightforward, whereas others are quite complicated. My goal here is to lay the foundation, provide you with some examples so you can at least understand what these things mean. Certainly by no means does this mean that you will be an expert after this talk. Some of the slides here are even 2 or 3 of the slides could be dedicated to an entire graduate course. Keep that in mind while we're going through this. So with respect to our objectives, there's going to be a pretest. So we'll go over 5 questions with the hope being that you guys can try to answer the questions beforehand before I provide the answers throughout the talk. There will be 4 main things we'll be going over, and then if we have time, we'll talk about the 5th thing. So firstly, we'll be talking about the null hypothesis, how you write one of those things and what we're trying to prove with that. We'll talk about the impact of an effect size. Importantly, we'll be talking about dichotomous and continuous outcomes and how to analyze both of those things. And then we'll be spending some time on non-inferiority trials and equivalence trials and briefly discussing the difference between a log rank and a Cox regression. And if we have time, we will very briefly touch on prediction models and perhaps how a researcher would come about making one of those. So quiz question number 1. Which of the following is an appropriately phrased null hypothesis? A, there is no relationship between steroid use and blood sugar levels. Option B, steroid use decreases blood sugar levels. Option C, steroid use increases blood sugar levels. Or option D, steroid use has an impact on blood sugar levels. So that's the first question. Question 2. A study shows that drug A reduces mortality with a p-value of 0.05. What does this mean? Option A, you are 95% confident that drug A reduces mortality. Option B, there is a 5% probability that the effect found was due to chance alone. Option C, there is a 5% chance of type 2 error. Option D, both A and C, or option E, none of the above. So third question, the student's t-test allows you to compare more than 2 means. True or false? Fourth question, the chi-squared test allows you to analyze dichotomous outcomes. True or false? And then finally, the last question, in linear regression, the dependent variable is continuous, whereas in logistic regression, the dependent variable is categorical. True or false? So with those questions out of the way, we're going to start with the null hypothesis. What is a null hypothesis and why do we need one? So in general, a null hypothesis states that there is no difference between the treatments being compared. So to give you an example, if we were flipping a coin heads or tails, like I've shown you on the slide here, the null hypothesis could possibly be that there's a 50% chance, 50% of the tosses that we're going to do are going to result in heads, and 50% of coin tosses we're going to do are resulting in tails. And if our experiment proves to be otherwise, then we can say we can reject the null hypothesis. However, if we end up getting a 50-50 split between heads and tails, then we have to accept the null hypothesis that there is no difference. So usually when you're designing studies, the null hypothesis is that there is no difference, and the results will bear out what that means with respect to whether or not we're going to accept or reject the null. So to carry on forward with this example of heads or tails with a coin toss, the purpose again is to accept or reject the null, which we said is a 50% heads and 50% tails. So if we do an experiment and we do a coin toss 10 times, and as a result, we get heads 10 times. So 10 times out of 10, we get heads. So based on that alone, you have no tails. We thought it was going to be 50-50. Based on that, the null hypothesis, we can reject it because we got the heads 10 times, or the null hypothesis being that the coin is unbiased. So now, with the result of 10 heads in a row, what's the probability of that happening? So, I mean, if you flip a coin, there's a 50-50 chance that it's going to be either heads or tails, right? So we can say the probability of getting heads is 50%, so that's 0.5. And what's the probability of that happening 10 times in a row? That would be 0.5 times 0.5 times 0.5, add that on 10 times, so 0.5 to the power of 10. So if you look at that overall, that's 1 in 1,000. There's a 1 in 1,000 chance that we're going to get 10 heads in a row. So, what's the precise meaning of this p-value here? It means is that if the coin was unbiased, by that we mean if the null hypothesis was true, and we were to repeat this experiment many, many times, to have 10 consecutive heads in a row would be expected to occur by chance in less than 1 in 1,000 of these repetitions. So this means that if I were to do this experiment 1,000 times, 1 out of 1,000 times, we would expect to get 10 heads in a row, and that would be purely due to chance. We're going to keep talking about this p-value very specifically, because if you don't know the concept of a p-value and you see certain studies, which I'm going to show you in the next slide, you may be led into thinking that there is in fact a result that's significant when in fact it's due to chance alone. So let's talk about a real life example from the ICES2 study, which looked at intravenous streptokinase, oral aspirin, or both in patients with suspected acute MI. This was published in the Lancet in 1988. As part of that study, if you may or may not be familiar, they found that there was a mortality benefit with aspirin and streptokinase. They did a series of subgroup analyses to prove a point. So what they wanted to do is they looked at zodiac signs. So let's look at all of the astrological signs that are there, Capricorn, Gemini, Libra, to see if there's any differences between mortality depending on your astrological sign. And lo and behold, if you look at table 1 there, they found that if you were a Libra or a Gemini, aspirin wouldn't really be helpful there. So there was no difference in mortality in aspirin versus placebo, but every other astrological sign, there was a benefit. So what does this mean? Does this mean that people who are Geminis or Libras should not be getting aspirin? Or is this a chance finding because we did so many subgroup analyses? So, I mean, that's exactly it. I mean, there's no statistical grounds or methodological grounds to say that people who are Geminis are less likely to benefit from aspirin. This is an example of having too many outcomes, doing too many subgroup analyses. If you have too many outcomes, or if you have too many subgroup analyses, you're increasing the odds of you finding a false positive or a false negative. So in this specific case, this would be a false negative result, correct? Because we would expect everyone to have the same outcome here. So this is a good example of a type 2 error. So in general, when you're reading scientific texts or epidemiological texts, they talk about a type 1 error or a type 2 error. And this picture is always stuck starkly in my mind, where a type 1 error is they're telling a gentleman that he's pregnant, whereas a type 2 error is when you're telling a very clearly pregnant woman that she's not pregnant. So type 1 is false positives and type 2 is a false negative. So all of that was to kind of hamper on what a null hypothesis and what p-values are. And we're going to keep talking about this moving on. So moving on, in the next slide, we're very briefly going to talk about an effect size. There's a lot of different trials out there with a large variable number of sample sizes that are determined based on the power a study needs to show an effect. Now, when you look at this table that I presented here to you, we're looking at different event rates of treatments. And now you can see that the control event rates on the left-hand side, 2 out of 4 for the first row, and so that's 50%. And the treatment event rate is 1 out of 4, which is 25%. So the relative risk reduction here is 50%. Now, if you look at the next few rows, the relative risk reduction remains the same because 500 out of 1,000 as a percentage is the same as 2 out of 4. So if you just stop there, if you only look at these numbers, you're not going to be getting a lot of information about what these results actually mean. So let's expand this table and let's look at the confidence intervals. So this is the exact same table, but we've added in the confidence intervals. Now let's start from the bottom up. So with the control event rate of 500 out of 1,000 and the treatment event rate of 250 out of 1,000 and a relative risk reduction of 50%, you can look at the confidence interval there of 43.5 to 55.9. So certainly there is a relative risk reduction there. Now you compare that to, let's say, the second row of 10 out of 20 versus 5 out of 20. Yes, your relative risk reduction is the same at 50%. But when you look at the confidence intervals, it's up to an 80% benefit, but also 14% harm. So all that to say that when you look at an effect size, you have to see how many patients were enrolled. I think everyone knows the bigger sample size you have, the more robust your results tend to be. But this slide was to show you that an effect size is not, needs to be taken in the appropriate context, and you really need to look at the confidence intervals here. And we will talk about confidence intervals and p-values moving forward as well. So I'm going to stop there with effect size. There's definitely more reading to be done there. A lot of these tables that I'm going to be bringing up are from the User's Guide to the Medical Literature, which I've talked about in my last talk by Dr. Guy, Dr. Cook, Dr. Mead, and many others. So I'm going to show that reference at the end. So if you haven't purchased a copy of that book or have a copy from your institution, I would highly recommend that you get that book. So let's move on to different kinds of outcomes. We're going to talk about dichotomous outcomes next. So I'm going to start with an example. This was a study that my colleagues and I did assessing mechanical ventilation practices in the emergency department. It's a single center retrospective cohort study done here at McMaster University. What we wanted to see was, for patients who are intubated in the emergency department, prior to going up to the ICU, patients can sometimes wait in the ER for hours, and oftentimes the respiratory therapist isn't readily available to make, minute by minute or hour by hour ventilatory changes in the emergency department like they can in the ICU. So we were wondering, do initial settings have a bearing on patient important outcomes down the line? So we wanted to look at the impact of these settings on mortality and duration of mechanical ventilation. So for the dichotomous side of things, we're just going to talk about mortality for this part of the talk. We defined hyperoxia as being on a fraction of inspired oxygen of greater than 40%, with SATs greater than 95%, and a high tidal volume was defined as greater than 8 mils per kilogram. So what did we do? What did we find? Now, this is a dichotomous outcome, and we wanted to look for a test of association. So we used the chi-square test. Chi-square test can be used for dichotomous outcomes, and what you're doing is you're looking to determine if there is a statistically significant difference between the observed frequencies or the expected frequencies. Now, this is a test you can simply do quite readily and quite easily on SPSS. Again, the purpose of the talk is not to teach you how to do these statistical measures. It's more to expose you to what tests exist and for what outcomes we're using these for. So the chi-square test is a test of association for dichotomous outcomes. So the null hypothesis being there that there is no association between hyperoxia and mortality, and then the other null hypothesis being that there is no association between high tidal volume and mortality. So what did we find? So if you look at these two graphs, we found on the left-hand side is the graph comparing mortality to different tidal volumes. And if your tidal volume was less than 8 mils per kilo, your mortality was around 31%. And if your tidal volume was greater than 8 mils per kilo, your mortality was at 41%. So, when you look at the effect size, you're like, oh my goodness, there's definitely is an impact. But however, when you look at the relative risk, it was 0.75 and the confidence intervals overlap 1. When your confidence intervals overlap 1, that's one of the strong indicators saying that your results were not significant. So as a surrogate for a p-value, always good to look at the confidence intervals and to see if they cross the boundary of 1. Now let's look at the same test done on the right, but looking at hyperoxia and mortality. So we found that if you did not have hyperoxia, your mortality was 25.9%, and with hyperoxia, your mortality was 42%. So the relative risk there being 0.57, so a relative risk reduction of 43%. And you can see the confidence intervals there of 0.34 to 0.96, indicating that this is a statistically significant result. So moving on to the next part of dichotomous outcomes, we're going to talk very briefly about logistic regression. There is an entire graduate level course on regression, so I'm by no means an expert, but I'm going to provide you with some examples and again, give you some context. So this is a study done by the Canadian Critical Care Trials Group led by Dr. Deb Cook here at McMaster University, published in the New England Journal of Medicine in 1994, where they wanted to look at risk factors for gastrointestinal bleeding in critically ill patients. So just to give you an idea, regression examines the strength of a relationship between one or more predictor variables and a target variable. So we're looking at gastrointestinal bleeding and seeing what factors are at play that can impact that outcome. So for this specific study, they found that there were, if you look at the left-hand side of the table showing simple regression, so that was univariable logistic regression. Again, you don't need to know how to do this. But when they did this initial test, they found that there were many different risk factors that were associated with bleeding. So mechanical ventilation, coagulopathy, sepsis, liver failure, renal failure, enteral feeding, steroid administration, right? You can look at all of those p-values less than 0.001, and even the other ones, hypotension is 0.03, anticoagulation therapy, or organ transplant. So that was simple regression, still logistic. Now, when they did a multi-regression model where they looked at all of these outcomes together, what they actually ended up finding using this was that the only two risk factors here that are directly related to mortality is actually mechanical ventilation and coagulopathy. And whereas all of the other risk factors that we thought were related to mortality are actually related to both mechanical ventilation and coagulopathy, right? So all of the variables predicted bleeding in the univariate analysis were correlated with either mechanical ventilation or with coagulopathy, right? So then when you put them in the multiple regression model, you could not find any statistical significance. Again, this is very complicated. All I'm trying to say here is that for dichotomous outcomes, you can use complex modeling like logistic regression to see if there's a relationship there. So I'm going to switch gears from this to something called the receiver operating curve. I know our objectives are all over the place, but the goal here again is to expose you to these different topics. And I feel like a receiver operating curve or a ROC curve is very practical for clinicians as it impacts our day-to-day testing, particularly in the emergency department. So let's get started. A ROC curve depicts the power of a diagnostic test. So I'm going to show you some examples. And the big thing here is you have to be really familiar with your 2x2 tables, which I'm going to show you next, looking at your true positives and your false positives. And in general, a ROC curve plots your true positive rate, which is sensitivity, with the false positive rate on the x-axis, which is your 1 minus specificity. And the larger the area under the curve, the better your test is. And if the area under the curve is only 0.5, that is a useless test. So on the next slide here, this is a 2x2 table. I'm sure you all are familiar with it, but this is just here for your reference, looking at your true positive, your false positives, your false negatives, and your true negatives. And then there's the formula there for sensitivity and specificity. I'm not going to spend time on this. This is here for your reference. So let's go back into receiver operating curve, and I'm going to show you what I was just talking about a minute ago. So this is an example of a ROC curve. So you can see at the bottom, it says false positive rate on the x-axis. So that's 1 minus specificity. And on the y-axis, it's labeled the true positive rate, and that's your sensitivity. And you can see the blue dot in the top left is the perfect classifier, because if your blue dot's there, the area under the curve would be very high, would be as close to 1 as possible. And then if now in contrast, if you have the red dashed line, which is a level of 0.5 area underneath the line, that's not a very helpful test at all. So as you get closer to the blue line, the better off the test is. As you get closer to the red line, the worse off a test is. So I'm going to give you an example, so hopefully you guys can remember this. So there was a study published in the New England Journal of Medicine looking at sensitive troponin I assay testing in the early diagnosis of myocardial infarction. Most of us are using high sensitivity troponins these days. I suspect you are too. So on the right-hand side is a ROC curve, and you can look at the different things it tested. So if you look at a troponin I, it's the green line, and the area under the curve is in brackets. So 0.96, which is pretty darn close to 1, shows you how good of a test that is. Whereas let's say look at creatine kinase, which is the light blue line, has an area under the curve of 0.70, which tells you that the high sensitivity troponin is a far better test when it comes to its ability to delineate who has an MI and who doesn't. It's even better than a troponin T, which wasn't too bad to begin with an area under the curve of 0.85. But this is just here to show you the diagnostic power of a ROC curve. So we're going to switch gears here now. We talked about dichotomous outcomes. We talked about the ROC curve. We are now going to move on to continuous outcomes. So let's go back to the example that I used earlier about the study that we did looking at mechanical ventilation practices in the emergency department. So we had talked about our dichotomous outcome of mortality. Now we're going to look at whether ventilator settings in the emergency department have an impact on the duration of mechanical ventilation, which is a continuous outcome. So when you're looking at continuous outcomes, you have a number of different statistical methods in your arsenal. But for this one specifically, we used the t-test. So the t-test compares the means of two independent groups in order to determine whether there is a statistical evidence that the associated population means are significantly different. So what, if I were to say that in common speak is, if we were looking at hyperoxia, like we talked about, or lung protective ventilation, you have a group of individuals who got that and a group of individuals who didn't. So they're independent, and this t-test will determine whether or not that was actually the duration of mechanical ventilation was impacted by tidal volume or by hyperoxia. And in this instance, when we ran the t-test again on SPSS, which, like I said, again, the objective here is for you not to learn how to do these tests, just to know when to use one and that they exist. And you can look at our p-values there. So there was no difference found in duration of mechanical ventilation of the tidal volume with a p of 1.00 or hyperoxia with a p of 0.56. Okay, so a t-test, there's multiple different kinds of t-tests. It depends on your sample. There's a 1-sample t-test, there's a 2-sample t-test, there's a paired t-test. This table is here for your reference that you can come back and take a look at. But again, for these sorts of things, it's always wise to have a methodologist or someone with statistical expertise to help you with your analysis. So we've talked about this t-test in particular, and the one that we used was the student's t-test because there was only one variable. Now we're going to move on to, the t-test can tell you if there's two, if there's one or two variables. What if you have more than two variables? What test do you use there? So therein you use the ANOVA. So it's the analysis of variance. So if you have more than two groups, if you have 3 or more groups, you have to use the ANOVA test. Now I'm going to give you an example here because otherwise these things are just abstract. So let's just say there were 200 individuals who ate a high cholesterol diet for 16 weeks. So they all ate it for 16 weeks, and then we separated them into 4 groups. Group number 1, they had 16 more weeks of a high cholesterol diet. Group number 2, they had 16 more weeks of a normal diet. Group number 3, they were given a drug and they were told to return to the normal diet. And group number 4, they were given a drug and they were told to continue a high cholesterol diet. And the outcome here was the percent of aorta that was covered by plaque. Now, when you have these 4 groups and you're trying to compare these 4 groups, you have to do then multiple t-tests if you were to stick with t-tests. If you did pairwise comparisons, you have to do 6 pairwise comparisons, 4 choose 2 from the good old statistical days in high school. So if you were to do that, you would have compounding error. So for every t-test, if your p was 0.05, you would then have to multiply that by 6. So you're losing statistical power. And therefore, in these instances, if you're comparing more than 2 groups, it's better to do an analysis of variance. And what that would allow you to do is to see if the mean percent plaque varied across combinations of drug and diet treatment. Again, this can be quite complex. You need the help of a statistician. I'm going to keep saying this over and over again, but a good idea for you to know when to use which test, so that when you're reading a paper, even you can say, hey, they used ANOVA. It makes sense. They compared more than 2 things, or if they did compare more than 2 things and they didn't use an ANOVA, you'd be like, that doesn't seem right. So we're going to move on from ANOVA and we're going to talk about linear regression next. We had talked about a different form of regression earlier, so let's talk about linear here. So simple linear regression is used to model the relationship between 2 continuous variables. And I'm going to show you an example next. So the objective is to predict the value of an output based on the value of an input. So really we're looking now into modeling, which we're going to talk about very briefly as well. So here's an example, again, from the user's guide to the medical literature. So this is a table, a graph, sorry, showing you the distribution of walk test results in a total sample of about 220 patients. So if you look at the different walk test results here, you can see, a lot of people were able to walk about 400 to 450 meters. Very few were in the left end, which is 50 to 100 meters, and very few were in the front end of 600 to 650 meters. And as clinicians, we're often interested in prediction. We want to know which person will develop a disease such as coronary artery disease, and which person will do well and which person will do poorly. So this is our baseline data, and we want to look at, say, what's someone's respiratory function and how that impacts their walk test results. So let's say we want to look at their FEV1, so their forced expiratory volume, in 1 second, and to see how that relates to their walk test. So if we were to do that, we get a bunch of scatter plots there. So you can see that you have a number of blue dots showing people's walk test results compared to their FEV1. And then you're able to use the formula and use the good old slope of y equals mx plus b, and you're able to draw a line up. So you're able to then thereby make a model of sorts, right? So you have an independent and dependent variable, and this regression analysis assumes a straight line fit. Okay, and the dependent variable here is continuous, and that's why this is called linear regression. So this would be used for a continuous variable walking is a walk test result is a continuous variable. So again, you don't need to know how to do this once again, but just good to know that if you are looking at doing regression modeling, linear regression works well for continuous models. So now we're going to switch gears and talk about some more basic methodological things, talking about different kinds of trials. And the reason why we're keeping this at the end is because the way those trials are designed really depend on what statistical tests they've used. So let's talk about non-inferiority trials. Non-inferiority trials are exactly what they sound like. They're one-sided in nature. You're not really saying, you're not asking yourself, is drug A superior to drug B? You're saying, is drug A non-inferior to drug B? So you're trying to determine whether a new intervention is no worse than a reference intervention, right? So when is this useful? This is useful if you can't give a control group a placebo. So if you're testing a new drug combination for AIDS, for example, you can't give one group of the population who has the disease a placebo. That's unethical. It's the wrong thing to do. But perhaps you want to see if this new drug, which is perhaps cheaper, is just as good as this expensive drug. So in that instance, you don't really care if that drug is better. You just want to know that it's similar, at least. You have a similar effect size, similar benefit, and ends up being cheaper for people, right? So you don't use this design when the standard is not consistently better than placebo. So for example, if you know drug A is better at treating for dementia and you want to use a placebo, you can't use that. You can't have that. You can't have that as part of this non-inferiority trial. So similar to this non-inferiority trials, you also have something called equivalence trials. And again, they're also very similar. The point being there is that you want to determine whether two interventions have a similar effect, right? So they're helpful when investigators want to see whether a cheaper, safer, or simpler intervention is neither better nor worse than a current intervention, okay? So that was our brief foray into non-inferiority and equivalence trials. I promise you we're almost done. We're very briefly going to talk about some more statistical techniques. So next, we're going to talk about the log rank test and how that plays a role in survival analysis. So survival analysis, a log rank test isn't necessarily only for survival alone, but it is often used for survival analysis. So when is this useful? We talked about a 2x2 table. We have one here, showing ligation, number of people who died with ligation therapy for bleeding esophageal varices and how many died with sclerotherapy. And it's helpful, you know how many people died with each therapy, but wouldn't it be more helpful if you knew when those individuals died? Did they die at day 1 or did they die at day 10? When was the separation? When is one therapy better at what time point? So when you're looking at, when you want to know when certain events happened, that's when you want to use a test like a log rank test. So for this example, specifically comparing ligation and sclerotherapy, you can see that the survival curve separated pretty quickly, like within the first probably 10 or so days. So you can see the separation of the black line and the blue line. So this is where a log rank test is helpful. These are things you'll commonly see in papers when you're looking at survival analyses, and it's always helpful to understand the context behind why they use certain tests. The next thing we want to talk about is the Cox regression technique. So how is that different? So it's a it's a regression technique that allows for adjustment for known differences in baseline characteristics. So just to give you an example, the survival analysis that we just showed prior can't use multiple predictors, whereas the Cox regression model can. So you can put in multiple different risk factors, for instance, that would then help you determine whether a therapy is actually beneficial or not. Again, this is a very complex topic that genuinely has an entire course dedicated to it. And many institutions, I know at McMaster is a whole course for regression, so I'm not going to dive too deeply into it. But I am going to end with very briefly talking about prediction models. So prediction models are very helpful for clinicians and for statisticians and researchers because it really helps you look at known variables and predict the perhaps unknown variables. So some of the things that we've talked about today, like the Cox regression model, is something that statisticians and researchers will use to build these models. So for instance, a Cox regression model can help you build a survival function and can tell you the probability of a certain event happening. So, when is someone going to die and when is that going to happen specifically based on what therapies are on, depends on what risk factors they have. So, once you have the underlying statistical background expertise, you can then build on that and build these complex models that can really help you impact patient care on a much deeper level. So references wise, a lot of what I talked about came from the User's Guide to the Medical Literature. I plugged this in before, but I'm going to plug it in again. If you don't have this book, I think it's really important to get. It's by many authors here from McMaster. And again, thank you so much for inviting me and for allowing me to give this talk. My email address is sameer.sharif@medportal.ca. It was on the first slide. There's my Twitter handle. If you guys have any questions, I'd be more than happy to take them. And again, there's a lot of dense material here. I apologize, it's the topic assigned to me. Again, the goal here is not that you understand everything that that you not know exactly how to do all of these tests, but now you have a rough understanding of when to use certain tests and when not to use certain tests. And hopefully this will not only help you perform research in the near future, but also allow you to better understand the things that you're reading that's informing your clinical practice. Thank you so much.
Thank you, Dr. Sameer, for giving us that concise yet well laid out outline of the various methods used to analyze dichotomous as well as continuous variables. As mentioned by Dr. Sameer, the purpose of the lecture is to determine where certain analyses are used and like what goes where, essentially, rather than understand the entirety of their application, which honestly is sometimes beyond even the most seasoned researcher. So that wraps up our lecture sessions, which means it's now time to move on to our live Q&A segment. May I please request our speaker, Dr. Carlos, to kindly switch on his microphone and video. Dear audience, please feel free to type in your questions related to the topics discussed today in the chat box, and Tasnim and I will read them out to the speakers.
Yeah, I'm having a little problem with my video. Can you hear me though?
Yes, Dr.
Yeah, we can hear you, Dr. Carlos. Yeah.
I think we're going to have to try to do this without video. And I'll try to work with you guys as I can, okay?
Is it that you're not able to share your video, or it's a technical issue from your side?
The camera seemed to have just stopped working, and I think I want to spend a lot of time trying to get it to work right now.
Yeah, no worries.
So let's
Yeah.
let's just move on to the questions. Apologize.
Okay. Welcome, Dr. Carlos. Again, this is Tasnim, the host for today. And our first question is actually for you. And it says that you had mentioned how the p-value or the chances that a result was due to the studied intervention or variable, rather than by chance, have a higher degree of accuracy once the sample size is increased. Well, this makes sense, especially with the whole NMR example. But while saying add a lot more participants to the study is obvious, by how much really part sometimes has some people confused. So is there a way to determine the best fit sample size based on the research question or the type of the study, for example?
Yeah, so that's actually a really good question, and it's a really complicated answer too, because basically what you're asking is how to do a power analysis and how to calculate the number of subjects. Let me see if I can at least share my screen, because I thought that what question was complicated enough that I should probably just get a couple of things together. I don't know if this is going to work.
Yeah, I'll give you the control to share your screen. Just a second.
Let's see if this will work. If it doesn't work, it's okay. I can just talk briefly about it, but.
Okay. Okay, I'll stop sharing from my side, and then you can share it from yours.
It's not working. Let me see. Nope. It says the host has disabled participant screen sharing.
Okay, try again, Dr. Carlos.
All right. I think, does that work? Is it working?
Yes, yeah, we can see it now.
Oh, I can't see what I'm doing though.
You just open the
Okay.
window. Yeah.
I don't know what I'm doing, so you guys will have to guide me here. My Zoom screen disappeared. Okay, so the question is, how to calculate sample size. And what I did was I actually cut and pasted a few things. Somebody along that question, so one of you asked, what's the formula to calculate the sample size? The formula to calculate the sample size is here. And so the simple answer to that would just be paste this on and say, well, guys, here's a formula. And the formula is, so for the difference between two means, you would look at the Z statistic for your alpha plus the Z statistic for your beta, which is typically 1.96 and the other is 1.28. And then you want to square that. Then you're going to multiply that by the square of the standard deviation of the samples, of the population samples, and you're going to divide it by the difference between the means. So as far as a form, there's a bunch of formulas. This is one of the easiest ones. I don't feel that it helps at all to understand what the importance is of sample size. And honestly, if you are going to calculate sample size, you really should resort to a statistician, or look at one of the better elaborate formulas that you have. If you type this into Google and you look at one of the reputable statistical sites, because you'll see that the numbers are way off depending on what you do. The important thing though is to understand the formula, is to understand what are you inputting here. And I think really the best for that is to sort of start with, what does power analysis mean? And what we're trying to do is we're basically looking at what you have to establish your alpha value, your beta value. In other words, you want to know what your chances of committing a type 1 error, a type 2 error, and then just plug in some numbers. So this is the way I find it easier to understand. What you're trying to look at is to see if the sample means between these two groups are actually different from each other. And the way to do that is you plug in your type 1 error, which is typically 0.05, your type 2 error, which you're going to establish depending on the power. And then you're going to look at the effect size. And I think the important thing to know is the effect size, because the alpha and the beta, you're going to establish a priori, and the effect size is going to depend on your population. So let me just go through this one more time to see if it kind of sinks in a little bit easier. First thing, what is the alpha value that I want? And typically that's going to be 0.05. For your power value for your beta, most of the time you're going to choose 80%. Sometimes you're going to choose 90. Now for the effect size is a composite. It's basically a formula that takes in the difference between the means. So you want to know what the difference is. Let's say you have a group of patients that are treating headache, and you're looking for a difference in the visual scale of pain, visual pain scale. And let's say that you consider a significant difference of 5. So your difference between the means that you're looking for is 5. And that's how you estimate that. If there isn't anything in the literature, you might have to run a small pilot trial. And I've done this before, especially in lab research when we were doing something no one's ever done before. We did a small trial with a few samples. We saw what the difference was, and then we estimated that would be the average difference. So you plug in the estimated difference of the means, and then you have to have an idea of what the standard deviation is for your population or your samples. And that's where a lot of the issues lie with trying to get the right sample size, is sometimes you don't know. And you can do just the best guess based on data that's out there, best guess data on data that you collect, or best guess by talking to a bunch of experts. But the fact of the matter is the effect size formula is just the difference between the means divided by the square root of the 2 standard deviations of your sample divided by 2. So that is the formula. And you plug in the power, you plug in your alpha, you calculate your effect size. In this case, for example, the example here is a difference of 10 with a sample, I think it's 7 and 9, I think. I can't remember the exact number, but you plugged in these numbers here and you came up with a effect size of 1.5. So now you have your power, you have your alpha, and you have your effect size. All you have to do is you go into any statistical website, you plug in these three numbers, and boom, you've got your sample size, your estimated sample size. So at least you'll have an idea if you're going to need 30 or 300 patients for your study, and that'll kind of get you set off. But you have to sit down with a statistician, because as you can see, there's going to be a bunch of things to discuss about this, sort of standard deviation of the population, the variability of the population. And then that is just a statistical aspect, right? The other aspect that you have to look at is, how much is this going to cost me? How many patients can I actually get? How reasonable is it to look at to get these numbers? Sometimes I just won't be able to get these numbers. I won't be able to get a difference of, let's say I need 600 patients to find a difference of 10. So maybe I'm going to look for a difference of 5. And so all these things come into play when you look at the size. Does that answer the question?
That was very helpful. I think the illustrations were very, very informative. Our colleague here, Jonathan, is asking how to get a copy of it, if it's possible to share it with us, and then we share it with you.
I can share this. Sure, this is just a website. Yeah, I can share.
That was amazing, Dr. Carlos.
I will stop sharing my screen now.
Yes, sure.
Okay, thank you, Dr. Carlos. Our next question is for Dr. Sameer. Unfortunately, Dr. Sameer is unable to join us for the live session, but I will read out his response. So here goes the question. We frequently encounter odds ratio and risk ratios in academics, but often likelihood ratios gets a bit overlooked. So in your lecture, in Dr. Sameer's lecture, he mentioned regression models, ROC curve, which is the receiver operator characteristics curve, and prediction models. And one thing that usually pops up in papers using these is likelihood ratio. Now, of course, these are more used in diagnostic studies, but what would be a good way to briefly describe the utility of likelihood ratios and their importance in analyzing data? So Dr. Sameer has prepared a response for us. You're right in that likelihood ratios are most useful when it comes to the process of diagnosis. The likelihood ratio for a particular test helps us to move from a pre-test probability to a post-test probability. Now, an LR of 1 tells us that the post-test probability is exactly the same as the pre-test probability. LRs greater than 1 increase the probability that the target disorder is present. On the other hand, LRs less than 1 decrease the probability of the target disorder. Now, there's an example which he has shared with us. For example, for acute appendicitis, the positive likelihood ratio for CT is 13.9 and negative likelihood ratio is 0.09. With a likelihood ratio positive, which is that high, now our post-test probability after a positive CT for appendicitis is quite high. Thus, we are quite confident that after a positive CT, our patient does indeed have appendicitis. And similarly, with a low negative likelihood ratio, a negative CT for appendicitis would decrease our post-test probability of the patient having appendicitis. Now, as such, we would be quite confident that for a patient with negative CT, they do not have appendicitis. Thank you, Dr. Sameer, for your response. Dr. Carlos, do you have any comments to add for likelihood ratios?
No.
Okay. So we move on to the next question.
Right, and next question is also for Dr. Carlos, and I think probably you are better aware of this, but there has been a lot of recent debate on our over-reliance or rather fixation of the p-value being less than 0.05. so much so that the value itself has been used to mirror findings from a paper. So obviously, what should not be the main focus of the study results. Can you elaborate on how the p-value may be skewed or perhaps misinterpreted in research?
Sure. I guess there was a couple of other issues you guys had requested to talk about p-hacking as well as part of that answer. And what I wanted to say is, so p-values are still very important. There's been a lot of focus now on reporting everything in confidence intervals, which I believe still is superior to reporting just a p-value. But that doesn't diminish the value of being able to precisely state if something is significant or not when you want an answer like that. And so I guess the fine detail is when you want an answer like that. When you report just a point estimate, you give just information about is it significant or not significant. On the other hand, when you expand that to a confidence interval, in addition to everything that's on the p-value, you're going to give everyone a size, and that's on my presentation, but you're going to give a good information about the size of the treatment difference. So therefore, for example, let's say I'm testing 2 blood pressure medicines and I find out that the difference between the 2 of them is, I'm going to make this up, 25 millimeters of mercury. It's a huge difference in treatment. And if I give you just that value, 25, and I say it's statistically significant, you're going to say, wow, this is a great drug. But if I tell you that the confidence interval goes from -5 to 45, then you're going to say like, okay, wait a minute. Not only does that threshold cross 0, which may mean that there's no difference at all, but that's a very wide difference. And being so wide, being so little precise tells me something about the data. It tells me, well, maybe the sample size wasn't big enough, or maybe, there just wasn't enough information available for them to draw that conclusion. So they did a few patients only. And so it changes the way you look at that p-value. Also, let's say that you get a negative result. You can say, well, they got a negative result because the sample size was too small. So adding a confidence interval really is a significant benefit to just reporting the p-value. The other thing also is that it kind of helps you find out if the authors were p-hacking, when you do a confidence interval, because if the authors are reporting a bunch of p-values just close to 0.05, 0.045, 0.049, when they start putting these confidence intervals, you can say, wait a minute, but all these confidence intervals are super wide here, or this is obviously, something that doesn't make a lot of sense, which is easily visualized as opposed to just trying to guess looking at p-values. So p-hacking is an issue that happens when you just report p-values, and it's a lot more difficult with confidence intervals. And just to kind of answer the last part of that p-value question, I would say the best way to avoid things like that as a researcher yourself is to just a priori establish the outcome measures that you're going to look at, establish the sample size, and that way you can't just say, I'm going to add on 5 more patients to this sample size to get a statistical value at the end. You've already determined before that, and that's good statistical practice, good research practice. So I think that's what I had to say about p-values and confidence intervals.
Thank you so much, Dr. Carlos. This was helpful. If any other questions for Dr. Carlos, our dear audience?
Yeah, we still have time to take a few questions from the audience if anyone has any questions related to the topics discussed today. Okay, so I think that's about it. That was our last question. So this brings us to the end of module 5 for the research work plan. On behalf of the entire team of ECREM, I would like to thank both our speakers for their time, cooperation, and valued contribution to this academic initiative. Thank you, Tasnim, our host, for your continuous hard work behind the scenes. And thank you to each and every member of the audience for your participation. We hope this module will help demystify some of the concepts of data analysis, and see you all soon for module 6 of the research work plan, where we should discuss all things related to research presentation and dissemination. So thank you all for joining us today, and goodbye.
Thank you.
Thank you, Dr. Carlos. Thank you, Sania. Thank
Thank
you,
you.
audience. Yeah, see you in the next module.